Hey students, got another great question from chapter 17. So again, more on sound waves, and actually more on Doppler effect. So I've been getting a lot on Doppler effect, and maybe that makes sense. This is probably some of the hardest questions, and this is a two-step Doppler effect. This one's really interesting, at least part B, and that's really what the question is. But I need to go through A first. So let me just read the question. It says, to permit measurements of her speed, a skydiver carries a buzzer that emits a steady tone of 1800 hertz. Okay, so somebody's falling out of the sky. Let me not try to draw a person, but here's the ground level somewhere, and they have this transmitter making sound waves at 1800 hertz. So whatever the mechanical device is that she's holding, the actual, let's say it's a speaker, and so it's got a little diaphragm, maybe it's paper, plastic, whatever, but it's going back and forth 1,800 times per second, okay? But of course, she's moving downward, right? She's a skydiver, okay? And it goes on to talk about a friend who's down here listening to that. So it says, a friend on the ground at the landing site directly below listens to the amplified sound he receives. Assuming that the air is calm and the speed of air, so speed of air to be 343 meters per second, so somewhere around room temperature, and independent of altitude, okay? Probably not real true there because it does get colder as you go higher in general. Well, the skydiver is falling at her terminal speed, so that's pretty good. We don't have to worry about her speeding up. She's already at her terminal speed, so she's dropping at some speed v. Maybe I'll even put a sub t for terminal speed. That way I won't confuse it with the v for the speed of the sound waves. While the skydiver is falling at terminal speed, her friend on the ground receives a frequency of 2,150 hertz. Okay. And so the first part is, okay, what is the skydiver's speed of descent? So what's the skydiver's terminal speed? All right, let me just write it out again. Doppler effect. The perceived frequency is the original frequency and then shifted a little bit. And how much it is shifted is a function of how fast things are moving. One could be the observer, the other one could be the source. And so when the observer moves, it's as if the waves are traveling faster. So it goes in the numerator where speed goes when you have something like frequency equals velocity over wavelength. But then if the source is moving, it crunches them together or spreads them out. So it's as if the wavelength is changing, but the speed of them is still the speed through the air, irregardless of the speed of the source. So that's why we would modify the downstairs. So if wavelength is modified, we put something downstairs, and if velocity is modified, we put something upstairs. Okay, and as you might have seen me do a few other times, we can write the situation if things are moving toward each other or if things are moving away from each other. And if they are moving towards each other, it would be like a faster speed, or if they're moving away, a slower speed. So the upper sign when the observer is moving towards the source, and the minus sign when it's moving away. And then likewise down here, if the source is moving towards, we should have a minus sign and then a plus sign. And so we just got to decide which one is moving, okay? And in this particular problem, it's kind of interesting because, at least in A, only one of them is moving. It makes it a little bit easier. Okay, so they say the person on the ground is receiving it. So the person on the ground is the observer. So no speed for that one. They're saying their perceived frequency is 2,150. The real frequency, that is the real mechanical frequency, the rate at which something is vibrating back and forth, is 1600. And so in the numerator, I'm going to put a speed of 343, since that's what they say to use. So whatever that temperature that corresponds to, something very close to room temperature. But there's no plus or minus, 0 here. There's no, I can't really say towards or away, but it's just 0 speed. So the observer isn't moving. But what is moving is the source. The source is falling downward at some terminal speed. So this would be the speed of the wave, 343. And they're moving towards each other, so it would be a minus. And then this would be the magnitude of the speed of the source, which is that terminal speed. And that is the question for A. That's not really the question that was emailed to me. The question you need to know is how do I do B? But the A is the parts that I need to do first here. To find the skydiver's speed. Okay, so now I can get out my calculator. And I thought I grabbed my better calculator. And I have misplaced my better calculator. All right, well, this will be the backup here. Okay. Yeah, I just did this in the last problem I did a little while ago. And went and grabbed my new calculator and still misplaced it. All right. So let me go ahead and use this old calculator here. I'll start here with 2,150 divided by 1,800. And I get a number of 1.19 for repeating. Okay. And that would be 343. And then this would be 343 minus the terminal speed. Or rearranging it, 343 minus the terminal speed equals. And so let me just take the 343 in the numerator here, divide it by the last answer. And I get 287.2. Move terminal speed over to the right and go 343 minus that last answer. And I get a terminal speed of 55.8 meters per second. And so that's the speed at which the skydiver is falling. Okay. Keep that in mind as I turn the page here and go on to B. I'll call this page 2. And let's read that one together. So that one says, let me find B. Where's B? Where'd it go here? Okay, what if? Okay, now suppose the skydiver can actually hear the sound of her own buzzer that is reflected off the ground. What frequency does she receive? Well, again, this is a Doppler effect. So let me just write out the equation, speed of the observer, speed of the source, and a plus if they are moving towards each other, a plus and a minus downstairs, or a minus and a plus if they're moving away. Okay, and then I'll even put for clarity here, okay, toward, away. Now, the thing to think about in this problem then is what is the source and what is the observer? I would say, again, the source is the little buzzer she's holding, but the observer is the ears on the skydiver. This time it's not the observer, is not the the person on the ground, which they call the he. The observer is the skydiver herself. And so in that case, I would say that there's motion to both of these. The source is moving and the observer is moving. And I would say they are moving together. I would say they are moving towards each other. Now, in this, they don't always have to move towards each other, but in this case, they are. I mean, they're essentially one and the same because she's holding the source here. So I guess I'd put this. The legitimate frequency is the 1800 hertz that they told us about. And the velocity of the sound waves is the 343. And maybe I'll start here with the observer. So the observer is actually the ear on the skydiver. And as it's kind of hard to kind of imagine this, I think. Maybe the way to think about it is something like this, is maybe a mirror image. Here's maybe the source, here's the ground, and it bounces off and, kind of reflects. If you think of that as not reflecting, but being a mirror image here, what's happening then is the source is moving towards the observer, but also the observer is moving towards the source. So both of them are moving. And so I would use the plus sign in the numerator and the minus sign in the denominator here to figure this out. Okay. Okay, now the speed, of course, is the same because, again, the observer, the skydiver, she is actually holding the source. So the source has got to be moving at this speed of 55.8. So I'm going to put a 55.8 in for both the speed of the observer and the speed of the source. And now I can do a calculation. So in the numerator, 343 plus 55.8. And in the denominator, actually, why don't I just go divide by, and in the denominator would be 343 minus 55.8. And so that's the fraction, about a 39% increase. So finally, the last step, multiply by that original 1800, and we're looking at 2,499 hertz, excuse me, for the perceived frequency. Now, by the way, there is kind of a fun way to also do this, especially since we already did A. You could just think of the reflection off the ground as being the new source. And as we did in part A, that source has a shifted or perceived frequency of 2,150. So if you wanted, you could do something like this, and maybe this would make more sense for some of you. But I thought it would be nice to show both of these. Is that you could then say that the frequency, oops, I'm going to put a asterisk there. The frequency of the source is coming from the ground. Now, granted, that is a frequency that is already shifted from her original source. So that might seem a little confusing, but it works great. It is just, look, this is all you care about. It actually is coming off the ground at this frequency. And of course, then you're going to be moving towards it. So in this case, the observer is moving. So this would be 343. And the observer, the skydiver, is then moving towards this source. The observer is moving. And then, of course, you would say the source is the ground, so you would say the ground's not moving. So this would be an alternative way, and actually would be a good one in this case because we just got done with A, and they said what that frequency would be off the ground. And so you, again, not going all the way back to the original sound, then it's shifting, but then taking it, it's already shifted, and it's just going from the ground on up. Okay, so then we can calculate this perceived frequency. And we better get the same thing. So this is 343, add 55.8. Divide that by 343, and this is a shift of about 16%. So it's 16% of what's coming off the ground. What's coming off the ground, quote unquote, our new source, is 2,150. And so sure enough, we get, although it rounds up one higher, so other than rounding, we're talking about the same real effect. Whether you go back to what I might call the original sound and then the skydiver being the receiving it, or you go back to thinking of the ground's reflection as being the source and the observer is moving towards that source and the source is not moving because it's the ground, you get the same number. All right, hope that helped.